What if I told you the fate of our planet could hinge on invisible rivers in the sky? Let's unravel the jet stream mystery and the chilling idea of an ice age. Imagine standing at the edge of space, watching ribbons of wind dance across our planet like luminescent snakes in the dark. These aren't just any winds. They're nature's own weather highways, cruising at speeds that would make Formula One drivers jealous. Welcome to the world of jet streams, where winds howl at a mind-bending 200 miles per hour and shape the very weather patterns we experience down here on Earth. These atmospheric rivers flow about 6 miles above our heads, precisely where commercial pilots love to play. And who can blame them? Catching a ride on these wind currents is like hopping onto nature's own bullet train, slashing flight times and fuel costs in one fell swoop. The next time you're on a flight from New York to London and arrive surprisingly early, you might just have hitched a ride on one of these invisible expressways. The birth of a jet stream is a cosmic dance between hot and cold air masses. Our planet essentially works like a giant thermal engine. The equator acts as a massive heating element, while the poles serve as cosmic freezers. When these drastically different temperature zones collide, they create powerful atmospheric pressure differences. Add Earth's rotation to the mix, and voila, you've got yourself a jet stream. These aerial rivers don't flow in straight lines, though. They meander across the globe in massive waves called Rossby waves, named after the Swedish-American meteorologist who first explained them. These waves can span entire continents, pulling Arctic air southward or tropical air northward, creating those weather patterns that make meteorologists scratch their heads and farmers check their almanacs twice. But here's where things get spicy. These jet streams aren't behaving like they used to. Scientists have noticed them getting increasingly wobbly, like a spinning top that's losing its momentum. The polar jet stream in particular has been meandering more dramatically than ever before, creating what meteorologists call blocking patterns. Imagine a river suddenly developing extreme curves and bends. That's essentially what's happening up in our atmosphere. These new patterns can trap weather systems in place for extended periods. Remember that heat wave that wouldn't go away, or that winter storm that overstayed its welcome? Blame it on these atmospheric traffic jams. When weather systems get stuck, they can transform typical weather events into extreme ones, turning a warm spell into a devastating drought or a snow shower into a record-breaking blizzard. The science behind these changes points to something called Arctic amplification. As global temperatures rise, the Arctic is warming faster than the rest of the planet, about twice as fast, in fact. This reduces the temperature difference between the poles and the equator, which is like removing fuel from the jet stream engine. The result? A weaker, wavier jet stream that's more prone to getting stuck in unusual patterns. The impact of these changes ripples through our entire climate system like a stone thrown into a cosmic pond. When jet streams wobble, they don't just affect local weather. They can trigger a cascade of events that influence everything from ocean currents to ecosystem timing. Migrating birds find their traditional weather cues scrambled. Plants bloom at unexpected times. Even marine life feels the effects as ocean temperatures shift in response to altered wind patterns. Think of jet streams as Earth's atmospheric orchestra conductors. When they wave their batons in familiar patterns, the weather follows along in a well-rehearsed symphony. But now, it's as if these conductors have decided to experiment with avant-garde compositions. The resulting performance is unpredictable, sometimes chaotic, and increasingly intense. The changes we're observing in jet stream behavior have led scientists down fascinating research paths. They're discovering that these high-altitude winds might be more than just weather makers. They could be key players in larger climate shifts. Some researchers have even begun exploring whether dramatic changes in jet stream patterns might trigger more significant climate transitions. As we unravel the mysteries of these atmospheric highways, one question keeps surfacing. Could these increasingly erratic jet streams be signaling something bigger on the horizon? The answer might lie in understanding how these wind patterns have influenced climate shifts in Earth's past, and what their current behavior could mean for our planet's future. The story of jet streams is far from over. In fact, their changing behavior might be writing the opening chapters of a new era in Earth's climate history. But to understand where this story might be heading, we need to dive deeper into the connection between these atmospheric rivers and the potential for major climate transitions. The jet stream's influence on our climate goes deeper than just pushing weather systems around. It might hold the key to understanding how Earth could experience dramatic temperature shifts. Throughout our planet's history, there have been moments when the climate changed rapidly, flipping like a switch rather than gradually transitioning. These sudden shifts have left scientists wondering, could changes in our atmospheric circulation trigger another major climate event? The connection between jet streams and potential cooling isn't as far-fetched as it might sound. These high-altitude winds play a crucial role in a complex dance with ocean currents, particularly the Atlantic Meridional Overturning Circulation, Amoc. Think of Amoc as Earth's oceanic conveyor belt. It carries warm tropical waters northward through the Atlantic, helping to keep Europe's climate relatively mild despite its high latitude. When jet streams become more erratic, they can disrupt this delicate balance. Their wobbling patterns can alter wind stress on the ocean surface, affecting how heat is exchanged between the atmosphere and ocean. More importantly, they can influence precipitation patterns and Arctic ice melt, potentially flooding parts of the North Atlantic with fresh water. This matters because the Amoc relies on a precise balance of temperature and salinity to function properly. Historical records show that when the Amoc has weakened or shut down in the past, it has led to significant cooling in the Northern Hemisphere. The most famous example is the Younger Dryas period, roughly 12,800 years ago, when temperatures in parts of Europe plunged by up to 10 degrees Celsius in just a few decades. Some scientists believe this rapid cooling was triggered by a massive influx of fresh water that disrupted the ocean circulation. Before we carry on, I'd like to know what's the worst-case scenario you think can happen from jet streams? Leave your comments below. Okay, back to the topic. Recent observations have set off alarm bells in the scientific community. The Amoc has shown signs of weakening, currently running at its lowest pace in at least 1,600 years. Combine this with increasingly erratic jet stream behavior, and you've got a recipe for potential climate disruption. It's like watching the early warning signs of a complex system starting to behave differently than it has for thousands of years. The mechanism connecting them to potential cooling involves several feedback loops. When they become more wavy, they can create persistent blocking patterns that trap cold Arctic air masses over certain regions for extended periods. These blocks can lead to increased snowfall, which reflects more sunlight back into space, potentially creating a self-reinforcing cooling effect. Moreover, disrupted jet streams can affect the position and strength of storm tracks. This might sound technical, but it's crucial. Storm tracks determine where weather systems travel and how much precipitation they deliver. Changes in these patterns could lead to some regions receiving significantly more snowfall than usual, while others experience unusual dry spells. The interaction between jet streams and ocean circulation creates what scientists call teleconnections, climate links between distant parts of the planet. When one part of this system changes, it can trigger a cascade of effects elsewhere. For instance, altered jet stream patterns over the North Atlantic could affect monsoon systems in Asia, which in turn influence global weather patterns. Some researchers have proposed that if these disruptions become severe enough, they could potentially trigger a rapid cooling event. The theory suggests that a perfect storm of conditions, weakened Amoc, disrupted jet streams, and increased freshwater input into the North Atlantic could create a cooling feedback loop strong enough to temporarily override the overall warming trend from greenhouse gases. However, it's crucial to understand that this wouldn't happen overnight. Even the most rapid climate shifts in Earth's past took decades to centuries to fully develop. The climate system has significant inertia. Think of it like trying to change the temperature of the ocean with an ice cube. You could add the ice, but it takes time for the entire body of water to respond. The relationship between jet streams and potential cooling events represents one of the most fascinating areas of climate research. It highlights how changes in atmospheric circulation could theoretically lead to unexpected climate outcomes. While the idea of rapid cooling might seem to contradict what we know about global warming, it actually demonstrates the complexity of Earth's climate system and the potential for surprising responses to environmental change. Scientists continue to study these mechanisms using increasingly sophisticated computer models and observational data. Understanding how jet streams could influence rapid climate changes isn't just academic curiosity. It's crucial for predicting and preparing for potential future climate scenarios. As we gather more data and improve our understanding of these complex interactions, we get closer to answering whether changes in atmospheric circulation could indeed trigger significant cooling events. The possibility of jet stream-induced cooling remains one of the most intriguing aspects of climate science, challenging our understanding of how Earth's climate system responds to change. It reminds us that while the overall trend of global warming is clear, the path there might include some unexpected twists and turns. The viral spread of the 2025 Ice Age prediction has captured the public imagination, but the scientific reality tells a different story. Current climate data reveals a planet firmly in the grip of warming trends, with global temperatures climbing steadily despite variation in jet stream behavior. The idea that disrupted wind patterns could plunge us into an ice age within months isn't just improbable. It fundamentally misunderstands how Earth's climate systems operate. Let's look at the hard numbers. Global temperatures have already risen by 1.1 degrees Celsius since pre-industrial times, with each decade bringing new heat records. Greenhouse gas concentrations have reached levels unprecedented in human history. These aren't just statistics, they represent a fundamental reshaping of our atmosphere's heat-trapping capabilities. The notion that jet stream changes could suddenly override this warming effect is like suggesting a small fan could cool down an industrial furnace. The relationship between jet streams and global temperature is complex, but it doesn't work like a light switch that can flip between hot and cold. While these atmospheric rivers can influence regional weather patterns and create temporary temperature anomalies, they can't overcome the basic physics of greenhouse gas-induced warming. The heat-trapping gases in our atmosphere act like a one-way mirror, allowing sunlight in but preventing heat from escaping. Climate models, which have become increasingly sophisticated over decades of development, take into account countless variables, including jet stream behavior, ocean circulation patterns, and greenhouse gas concentrations. None of these models, even in their most extreme scenarios, show anything resembling an ice age developing by 2025. The thermal inertia of our oceans alone makes such rapid cooling physically impossible. It's like trying to freeze a swimming pool in summer by adding a few ice cubes. What we're actually observing is far more nuanced. The warming Arctic is reducing the temperature gradient between polar and equatorial regions, which in turn affects jet stream behavior. This can lead to more persistent weather patterns and increased frequency of extreme events, both hot and cold. But these regional variations occur against the backdrop of a warming planet, much like waves on a rising tide. The misinterpretation of jet stream behavior reveals a broader challenge in climate communication: the human tendency to seek simple, dramatic explanations for complex phenomena. While it's natural to want clear-cut answers, Earth's climate system operates more like an intricate symphony than a solo performance. Changes in one component ripple through the entire system in ways that can take years or decades to fully manifest. Consider the atmosphere's current composition. Carbon dioxide levels have surpassed 420 parts per million, a concentration not seen in millions of years. This enhanced greenhouse effect creates a planetary warming force that would require far more than altered wind patterns to counteract. The idea that jet stream changes could somehow negate this fundamental atmospheric transformation is like expecting a pebble to stop a landslide. Historical evidence further contradicts the rapid ice age scenario. Even during past periods of dramatic cooling, such as the onset of the Younger Dryas, the transition took centuries to unfold. Our current climate situation is unprecedented. We're pumping greenhouse gases into the atmosphere at rates far exceeding anything in Earth's recent history. This creates a warming momentum that would take generations to reverse, even if we stopped all emissions today. The real story of changing jet streams is actually more compelling than the Ice Age hypothesis. These atmospheric rivers are becoming more unpredictable, creating new patterns of weather extremes that challenge our traditional understanding of seasonal expectations. This isn't leading to global cooling, but it is reshaping regional weather patterns in ways that demand our attention and adaptation. Looking ahead, the challenge isn't preparing for an unlikely ice age, but rather adapting to the reality of a warming world with more erratic weather patterns. The changes in jet stream behavior are one piece of a larger climate puzzle that includes rising sea levels, shifting precipitation patterns, and increasing frequency of extreme weather events. Understanding these changes requires moving beyond sensational predictions to grasp the complex interplay of atmospheric and oceanic systems. The scientific consensus is clear. While jet streams play a crucial role in our weather systems and their behavior is changing in response to global warming, they won't be ushering in a new ice age in 2025. Instead of focusing on unlikely doomsday scenarios, we need to understand and prepare for the very real challenges posed by ongoing climate change. The story of jet streams and climate change isn't about implementing frozen doom. It's about understanding how our planet's atmospheric systems are adapting to a warming world and what that means for our collective future. The changing behavior of jet streams serves as a reminder that Earth's climate system is incredibly complex, with multiple interconnected components that can produce unexpected outcomes. While these changes won't trigger an imminent ice age, they do underscore the importance of understanding and addressing the broader implications of climate change. As we continue to observe and study these atmospheric patterns, we're better equipped to prepare for the actual challenges that lie ahead, rather than being distracted by improbable scenarios. If you enjoyed this deep dive into the fascinating world of jet streams and climate science, don't forget to hit that like button and subscribe to the channel. Every week, we explore mind-bending scientific concepts just like this one, unraveling the mysteries of our universe, one video at a time. And remember, stay insanely curious.